grab a different pen here. So Taylor's theorem, the idea here basically is that we've seen how we can write lots of different functions as power series using our geometric series manipulation. Right, we know that we can definitely write that f of x equal to 1 over 1 minus x is 1 plus x squared plus x cubed, and so on, which is the sum from n equals 0 to infinity of x to the n, as long as x is, between 1 and negative 1. So definitely things that look like geometric series, we've seen ways we can manipulate, whether it's using the derivative, the integral, multiplication, right? We could write something like, g of x equal to x over 1 minus x cubed. We could write that as x times 1 over 1 minus x cubed. And then that's going to be x times the sum from n equals 0 to infinity of x cubed to the n. The question arises, though, what if the function doesn't look like the sum of a geometric thing, right? Like we've kind of locked ourselves in with this to having something that looks like 1 over 1 minus a ratio. Right? We can definitely deal with something where our function is some first term over 1 minus r. But if it looks different than that, we're kind of stuck. Well, there is a way we can find a power series for a function, and it's using Taylor's formula. So Taylor, I'm gonna, I'll erase this for now, but I'm definitely happy to come back to this if we figure out what the statement actually is. So there's just something that's not quite right there, I think. So here is Taylor's formula. So Taylor's formula says that you can write a function as equal to its Taylor series. And there are some small caveats that we have to kind of talk about. Right, if it converges to its Taylor, if the Taylor series actually converges to the function, sometimes it doesn't. Usually it's a weird example if it doesn't. But here's the formula for a function, for the Taylor series of a function. It's the sum from n equals 0 to infinity of the nth derivative of the function evaluated at the center c times x minus the center to the nth power over n factorial. So we start writing out the first few terms, right? This is going to be, so the first term is going to be the 0th derivative, so just the function. It's really windy out there. Times x minus c to the 0th divided by 0 factorial. 0 factorial is 1. And then the second term is going to be the first derivative times x minus c to the first divided by 1 factorial, which is just 1. Seems silly to write that. And then it goes on, right? The second term, or I guess the third, when n equals 2, you get the second derivative evaluated at c times x minus c squared divided by 2 factorial. And it just keeps going, right? The next term is the third derivative evaluated at c times x minus c cubed over 3 factorial. And so on and so on and so on. So for pretty much any function, if we can't do the nice thing where it looks like a geometric series, we can say, well, I've got a function. I know how to find its derivatives. I can write out its Taylor series this way. Your professor should all show you how this gets derived. I don't think I'm happy to show you how it's derived if you want, but I think our time might be better spent doing some examples. So let's do some examples. And then if you want me to show you how we actually get this formula, I can, although that's not like super important. So let's look at some examples. I wish I had more board space. Let's do this one. So example. Let's find the first 4 non-zero terms. So find the first 4 non-zero terms of, what have I got here? Of the power series for f of x equals to 1 over x squared centered at x equal to 2. Sorry, I should write c equal to 2, not x equal to 2. I will point out, right, I used a different term here. I said the power series. I could just have easily written, find the first 4 non-zero terms of the Taylor series for f of x equal to 1 over x squared centered at c equals 2. Taylor series, a Taylor series is a power series. And I guess every power series is probably a Taylor series, but like it's kind of like, you know, the Taylor series is a specific form. A power series can kind of be anything, whether it's this form or not. So to find the terms, we have to find these derivatives. So let's find some derivatives. Yeah, I guess I could write, sure. So I don't want to write the formula first, although I guess I could. So here's what I'm looking for. I'm looking for writing my function 1 over x squared as, so my center is 2, so I'm going to do f of 2, and then I'm going to do f prime of 2 times x minus 2, and then f double prime of 2 times x minus 2 squared over 2 factorial, and then f triple prime of 2 times x minus 2 cubed over 3 factorial. And assuming that all of those are non-zero, which I think they are, that'll be the first 4 terms of the Taylor series expansion for this function centered at c equals 2. So we have to find these derivatives. This is kind of, you'll kind of see, this is what makes the Taylor series expansion or using Taylor's formula to find series kind of a pain in the butt. Finding all these derivatives is usually kind of the not great part. Here it's not terrible, right? We have to not find the derivatives of x to the minus second. So f of x is x to the minus second. F prime of x is negative 2 times x to the negative third. The second derivative is going to be 6 times x to the negative fourth. And the third derivative is going to be negative 24 times x to the negative fifth. I do recommend, I personally think it's better to write the derivatives out before we start plugging in the center. So then f of 2 is going to be 2 to the negative second, which is 1/4. F prime of 2 is going to be negative 2 times 2 to the negative third. 2 to the negative third is 1/8. Negative 2 times 1/8 is negative 1/4. F double prime of 2 is going to be 6 over 2 to the fourth, which is 6 over 16, which is 3 over 8. And f triple prime of 2 is going to be negative 24 over 2 to the fifth, which is 32. And 24 over 32 reduces to 3 over 4, I believe. So then writing this out, we get that the first 4 terms, 1 over x squared is equal to, so f of 2 is going to be 1/4. And then f prime of 2 is negative 1/4 times x minus 2. And then f double prime is going to be 3/8 divided by 2. 2 factorial is 2, so 3/8 over 2 is 3/16 times x minus 2 squared. And then finally, f triple prime was negative 3/4. 3 factorial is 6. So we need negative 3/4 divided by 6, which is 3 over 24, which is 1 over 8. So to be negative, so negative 1 over 8, x minus 3 cubed. And that's the first 4 terms of this Taylor expansion for this function. Oh, sorry, not x minus 3. Ooh, x minus 2. Sorry about that. So this is the first 4 terms of the Taylor expansion of f of x equal to 1 over x squared centered at c equal to 2. And I guess I should probably use not an equal sign here, but an approximation sign, right? Because we are approximating this function. And something that I think is kind of interesting, that is definitely worth seeing, is how as you add on terms, your approximation gets closer and closer to the actual thing. This is where I think Desmos is actually kind of really neat. So let me guys show you this, and we'll do this a couple times probably. Let me grab this here, share. Yeah, share, okay. So we are approximating, sorry, I've got like a million things open here. Yeah, go away. So we're approximating this function, f of x equal to 1 over x squared near 2, right? So we want to try and get it close to this function at the center 2 right there, right? Which is that point there. So here's our first approximation. If we just use the first term, it's 1/4. Okay, so right at the point, it's not bad, but as you move away, right, clearly not a very good approximation of the function. But then if we add the next term on, which is minus 1/4 times x minus 2, we get a better approximation, right? That slanted line is certainly a better approximation of this function near 2 than the horizontal line was. Something to observe here. This is something you should all be aware of. The Taylor polynomial with the first two terms, right, where you have, or of degree 1, right, where you just have x to the first, that's the same as the linearization, right? You're literally just finding the equation, the tangent line at the point you're interested in. So first degree Taylor polynomial, linearization of a function at a point, same thing. But let's add the next term. So if I add 3 over 16 times x minus 2 squared, well, look at that. It's even better, right? So, I mean, it's only going to be good in the vicinity of your center, but the more terms you add on to your approximation, the better and better and further out the approximation is good for. So if I add the next term, which is minus 1/8 times x minus 3, so x minus 2 cubed, right? Look, even better. And so as you might imagine, as you keep adding on more and more terms, it just gets better and better and better. And if you could add the infinite series, right, if you could do all of them added together, you would actually get the whole entire function on the interval of convergence, which depending on what you've got, could be everything, could be some of it, could be very small. So kind of neat. So it really does show, right, you're literally approximating this function with this polynomial. And the more terms you have, the better it gets. Go ahead, Julian.
So when you say like the first 4 non-zero terms, you can still have x, like it's still including x in the answer?
Yes. Yeah. So whenever we're finding a power series or Taylor polynomial, same kind of thing, there's always going to be the variable x. So if I'm finding the first 4 terms, it usually means, well, not always, but it often means I'm going to have as many what's what I'm looking for, as many incidences where you get up to like x to the 3rd, although actually it can be different powers. But right, so I have the first 1, 2, 3, 4 terms, and yes, there's always going to be x's because every term after the first term should have x minus your center, so to some non-zero power.
Okay, thank you.
But yeah, we're using, right, this polynomial is approximating this function. And then if you actually wanted to approximate it at a specific value, you could plug in a value for x. Let's see here. Where'd you go? Examples I was looking at. Sure. Okay. So what if we did want the entire series for this, right? What if this is not like sufficient for us? We want to actually write the entire series for 1 over x squared as a polynomial. Well, also I should point out, right, 1 over x squared, not a polynomial, right? It's x to a negative power, which is not a polynomial. So how are we going to do this? Well, the problem is things get challenging. And so if I want to write out, we want the entire Taylor series for f of x equal to 1 over x squared, centered at c equal to 2. So how do we do this? Well, let's remember what it looks like. We're looking for this. The function f of x is going to be the sum from n equals 0 to infinity of the nth derivative evaluated at the center times x minus c to the nth power over n factorial. So really our job here, in fact, I guess we can even be more specific, right? Our center is 2. So we got the nth derivative at 2 times x minus 2 to the nth power over n factorial. What we really have to do is we have to find a formula or a pattern for this. We need a formula for the nth derivative at 2. And so this is where it's really you kind of want to write things out and you want to not simplify it to help us see the pattern. So let's write out our derivatives again and let's actually not simplify them. So our first derivative, our 0th derivative, f of x, is x to the minus second. Our first derivative is negative 2 times x to the negative third. I don't know why I put parentheses there, I just did. And now here's where I'm not simplifying. Our second derivative is negative 3 times negative 2 times x to the negative fourth. And our third derivative is negative 4 times negative 3 times negative 2 times x to the negative fifth. And our next derivative, let's do one more. Our fourth derivative would be, I saw someone do this the other day where they wrote IV for their fourth derivative. I thought that was kind of funny. Usually we use a parentheses with the number after you get past 3. The fourth derivative here would be, so the negative 5 comes down, you get negative 5 times negative 4 times negative 3 times negative 2 times x to the negative 6th. So it looks like we can find a pattern here, right? It definitely looks like it's alternating. Right? So if I want to find the nth derivative, so let's see. Ignoring the alternating part for a moment. When I get the fourth derivative, I have 5 times 4 times 3 times 2. When I have the third derivative, I have 4 times 3 times 2. When I have the second derivative, I have 3 times 2. First derivative, 2 times 1. It looks like when I get the nth derivative, I have that number plus 1 factorial. That looks about right? Because you don't need the 1. 4 plus 1 is 5. 5 factorial is 5 times 4 times 3 times 2 times 1 that we don't need to write. I also need the alternating part. I need a negative 1 to the n or n plus 1. Which is it? I don't know. Let's check. So if I plug in 4, I have a negative, 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 negative. That's going to be positive. So when I plug in an even derivative, I should get a positive result. So that means I want a negative 1 to the nth, because an even power will give me a positive result. Whereas an odd power, the third derivative, will give me a negative times a negative times a negative, which will be negative. So when n is 3, I'll get a negative 1 cubed, which will be negative. Looks good. And then I have the x to the, so the power here is negative, let's see, 6 is 2 bigger than 4, 5 is 2 bigger than 3, 4 is 2 bigger than 2. It looks like it's going to be n plus 2. So that's what's going to go in here, except we're going to replace x with 2. So we can say that the nth derivative evaluated at the center is n plus 1 factorial times negative 1 to the n times 2 to the negative n plus 2. Or if you prefer, you can write that in the denominator as over 2 to the positive n plus 2. But I really can't stress enough. Writing out your derivatives like this and not simplifying them along the way so that we kind of see a pattern is really the key to figuring out what this is. So then I've run out of room, of course. I guess I can erase this up here. So here's what we can say. We can say that 1 over x squared is equal to, so I'm just going to replace this with all that. So I'm going to write it as the sum from n equals 0 to infinity of, so my nth derivative at 2 is going to be all this. Let's write it as negative 1 to the n times n plus 1 factorial. Let's write the 2 to the n plus 2 in the denominator. And then I still have also this x minus 2 to the n, and this n factorial on the bottom. And it is typically in our interest to simplify this as much as possible. Here, notably, we can simplify the n plus 1 factorial over n factorial to just be n plus 1. So we can write this as the sum from n equals 0 to infinity. Sorry, infinity looks kind of stupid up there. Of negative 1 to the n times n plus 1 factorial over n factorial is just n plus 1 over 2 to the n plus 2 times x minus 2 to the n. And that's how we would write this. It's still a bit messy, but it definitely works. If you wanted to, you could also compare this against what we wrote for the first 4 terms, right? I know, so let me go back and just write them. The first 4 terms we had were, let me write them down here. 1/4 minus 1/4 times x minus 2 plus 3/16 times x minus 2 squared minus 1/8 times x minus 2 cubed. So if you start, if you plug in n equals 0, you're going to get 1 times 1 over 2 squared, which is 1/4. If you plug in n equals 1, you're going to get negative 1 times 2 over 2 cubed. 2 over 8 is 1/4, negative 1/4. If you plug in n equals 2, you're going to get positive 1 times 3 over 16. 3 over 16. So this is matching up with what we had from before, which is good. It should match up. Another problem, and then I'm going to take a water / use the restroom break. I'm an old man who has to use the bathroom all the time, apparently. It's just this. It's really right after lunch. I've usually drank too much fluid at lunch, and then I have to pee. Anyway, I know it's not super important. So the other thing I do want to mention here is we can also ask, what is the interval of convergence for this power series? Right? We might want to know that. So to find the interval of convergence, we do what we've been doing. We use the ratio test. So ratio test, we do the limit as n goes to infinity. Okay, it's going to be a little bit messy. The n plus 1 term, so that's going to be negative 1 to the n plus 1 times n plus 1 plus 1, so n plus 2 times x minus 2 to the n plus 1 over 2 to the n plus 1 plus 2 is n plus 3 times, or I should say divided by this, which is multiplied by the reciprocal. The reciprocal is going to be 2 to the n plus 2 over negative 1 to the n plus 1, x minus 2 to the n. Okay, let's do this fast. The negative ones to the powers don't matter at all because they're an absolute value. And the absolute value of negative 1 to a power is just 1, which is not going to change anything. So I just get rid of that immediately. X minus 2 to the n plus 1 over x minus 2 to the n. That's going to be x minus 2. And that's the only thing that has to really stay inside the absolute value. N plus 2 over n plus 1. And then 2 to the n plus 2 over 2 to the n plus 3 is just 1 over 2. The limit of this is 1. So we end up getting that this is equal to the absolute value of x minus 2 over 2. And for the ratio test to converge, this limit has to be what? Less than. Thanks. Yeah, exactly. So then we solve for x. We get the absolute value of x minus 2 less than 2. We get x minus 2 less than 2, bigger than negative 2. We add 2 to everything. we get 0 is less than x less than 4. So our interval of convergence is from 0 to 4, but we need to check the endpoints. Now, it seems pretty obvious to me that it shouldn't converge at 0 because 1 over 0 squared is pretty problematic. And if we plug in 0 for x, it's going to not converge, right? In fact, really, no matter what you plug in, if you plug in 0 for x, you get negative 2 to the n over 2 to the n plus 2. Whatever that is, it's going to be some sort of negative 1 to the n or maybe to the whatever. But really, either way, you're still left with this n plus 1. Whether this is alternating or not, as n goes to infinity, n plus 1 either is going to go to infinity if it's not alternating, or if it's alternating, it's going to go back and forth between positive and negative infinity. But this n plus 1 here, right, essentially fails the test for divergence. But I could plug in, right? If we plug in, sure. If we plug in x equals 0, let's see, I've got a sum of negative 1 to the n times negative 2 to the n over 2 to the n plus 2 times n plus 1. Negative 1 times negative 2 both to the n is just 2 to the n. So this ends up being the sum of n plus 1 over 2 to the n over 2 to the n plus 2 is just 2 squared on the bottom. And clearly this series is divergent because nth term test, right? Test for divergence, this stuff doesn't go to 0. And then similarly, if x is equal to 4, that's just going to be a positive 2 right there, which means then you're going to get something that's probably alternating. Still diverges by the test for divergence, since these things don't go to 0. Okay, so our interval of convergence here is really 0 to 4, exclusive of the endpoints. Okay, we're doing time. Yeah, we can do one more question before I need to grab more water. So let's look at a very common example. Maybe, you know what, I should grab some water before we do this next example, because this next example kind of carries through to lots of other things. So let me grab some water and pee real quick. Why not actually have you guys start this problem? You probably, if you've already talked about Taylor Maclaurin series in class, you've probably seen this one already. That's okay. So I want you to find the Maclaurin series. That just means it's centered at 0, right? That's just a fancy, not fancy. It's just someone's name. They're like, oh, I discovered this one. Taylor's like, I discovered them all. Maclaurin series is just a Taylor series where the center is 0. So find the Maclaurin series for f of x equal to e to the x. So again, right, it's going to be the sum from n equals 0 to infinity of the nth derivative at 0 times x minus 0 to the n over n factorial. So your job really, and it's not a hard job, is just to find the nth derivative of that function at 0. I'll be right back. Okay, so I imagine everyone was able to find it. I could pretend like you've already typed the answer in the chat because it's already there. But the nth derivative of e to the x, no matter what derivative you're at, is e to the x. And so the nth derivative of 0 is just e to the 0, which is 1. So e to the x is like the best one ever because it's super easy, right? Any derivative is just itself. So the Taylor series, sorry, the Maclaurin series for the e to the x is just going to be the sum from n equals 0 to infinity of the nth derivative of 0, which is just 1, times x to the n over n factorial. That is your Maclaurin series for e to the x. Erase that, erase this. And right, it's good to know the first few terms and remember what it looks like. This is 1 plus x over 1 plus x squared over 2. I often write just 2 instead of 2 factorial because 2 is equal to 2 factorial. And then x cubed over 3 factorial, and so on and so forth. And one thing that's worth kind of noting about this is if you take the derivative, well, what's the derivative of e to the x? E to the x. So the derivative of this should be itself, and it is. Take the derivative of 1, you get 0. The derivative of x is 1. The derivative of x squared over 2 is 2x over 2, which is x. The derivative of x cubed over 3 factorial is 3x cubed squared over 3 factorial. But the 3's cancel and you get 2 factorial on the bottom, right? Because 3 factorial is 3 times 2 factorial. And then you get 4x cubed over 4 factorial. But 4 over 4 factorial is 1 over 3 factorial, because 4 factorial is 4 times 3 factorial. So really this is equal to that. It's itself, which it should be, because it's on derivative. Interval of convergence. I feel like we did this one before, but we can certainly check it. So interval of convergence for e to the x equal to the sum from n equals 0 to infinity of x to the n over n factorial. The Maclaurin series centered at 0. I shouldn't have to say centered at 0 if I'm saying Maclaurin series. Maclaurin series implies you're centered at 0. If we take, again, the limit as n goes to infinity of the n plus 1 term divided by the n term, or times the reciprocal of the n term. Well, here we're just going to get the limit as n goes to infinity. X to the n plus 1 over x to the n is just x. And n factorial over n plus 1 factorial is just n plus 1. And that's going to go to 0, which is always less than 1, which means this converges no matter what x is. So the interval of convergence here is literally everything. And that's often the case for nice functions like e to the x that are continuous everywhere. It's not always the case, but it is often the case. The things that are kind of like nice continuous functions that are differentiable everywhere often converge to have an interval convergence that is everything. Yeah, cool. And is it time to talk about that yet? I don't think so, but we might be there soon. Yeah, let's look at a couple other special examples. There's never enough room. Okay. So this one, that one, e to the x, definitely worth memorizing. E to the x is on your list of Taylor series, Maclaurin series, whatever, to memorize. So far, here are the series that I think you should know by heart without question. 1 over 1 minus x, obviously. 1 plus x squared plus x cubed. Is that. And then e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial plus x over 4 factorial. You definitely want to know those ones by heart. And then I will also point out, not that you have to know these ones by heart, but you should be able to get to these ones. The natural log of 1 plus x, you can get to as the derivative, as the integral of 1 over 1 plus x, which is the integral of 1 over 1 minus x. And that you can write using this idea here. And similarly, the arctangent of x is the integral of 1 over 1 plus x squared, which you can write as the integral of 1 over 1 minus x squared. These are 4 very common power series. I guess I could say they're all Maclaurin series because they are all centered at 0. That you should be relatively good at getting. These 2 you should memorize. These 2 you should know how to get to in this way. Let's look at the next 2 examples, which I wanted to say, which kind of got distracted from for a second. So these next 2 are also ones that you definitely want to memorize. So again, and this is, I don't remember who was asking, but so let's find first the first 3 non-zero, and this is where it's going to be a little bit more important, non-zero terms of the Maclaurin series for f of x equal to sine of x. Sine and cosine are also fairly well-known Maclaurin series. So again, let's write out the pattern. So it's either, you can either write out this, right? It's the sum from n equals 0. Right? I'm always kind of starting with this. I know I'm looking for the nth derivative at 0 times x minus 0 to the n over n factorial. You can also write it out the long way. It's going to be f of 0 plus f prime of 0 times x over 1 plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial. We want to find the first 3 non-zero terms. So let's go ahead and find our derivatives. So our function is sine of x. We know the derivatives of sine, right? The first derivative is cosine. The second derivative is negative sine. The third derivative is negative cosine. And the fourth derivative, you're back to where you started at sine. So we've got this cycle here of sine, cosine, negative cosine, sine, cosine, right? And we can see that f of 0, sine of 0 is 0. And the first derivative is 1. And the second derivative, again, is 0. And the third derivative is going to be negative 1. And the fourth derivative, we're back to 0. So every even derivative is 0. And every odd derivative is either 1 or negative 1. It's going to go back and forth. So writing out the first 3 non-zero terms, let's see, f of 0 is 0. F prime of 0 is 1. F double prime of 0 is 0, so I don't get an x squared term. F triple prime of 0 is negative 1, so I get a negative 1 over 3 factorial times x cubed. And then I don't get a fourth power term, right, because that would also be 0. Or sorry, a fourth derivative would be 0. And the fifth derivative should get me back to being positive 1. So I'm going to get a fifth derivative, which is positive 1 over 5 factorial times x to the 5th. So the first 3 terms of the sine function, I should say the first 3 terms of the Maclaurin series for the sine function, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And I think we can see the pattern at this point, right? The pattern definitely looks like it's alternating and you get every odd term, right? So the next term would be x to the 7th, sorry, minus x to the 7th over 7 factorial. So we can see that sine of x, if we want all the terms, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And it just goes on and on and on. And we can write this as the infinite series from n equals 0 to infinity. We definitely want a negative 1 to the n, right? Because we want to be alternating. And we do want to start with it being a positive term when n equals 0. And then we want x to an odd power divided by the same odd power factorial, same odd number factorial. So I want x to be, well, the problem here is n is increasing by 1 every time. The odd, if you want just the odd numbers, you need to increase by 2 every time. So x to the 2n plus 1. So when n is 0, I get 1. When n is 1, I get 3. When n is 2, I get 5. Over 2n plus 1 factorial. And like e to the x, this also converges everywhere. I think I've got enough for both of these. So yeah, so sine of x is also one that you really would like to memorize. And it's the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Time is it? Okay. Oh, yeah, we got this all half hour. Cool. We should talk about the interval of convergence. So interval of convergence here. So here's kind of something you might start recognizing. If you have a series, and you found the sigma form of it, the summation form, there's another word for this, but the condensed form, right? Not the long written out form, but the formula one here. If you can see that the formula has like a division by something factorial, that's often a good sign that it's going to converge for everything. Because, right, if you look at the ratio test, the limit as n goes to infinity of the n plus 1 term, I'm not even going to write the negative 1 to the n plus 1 because we know those don't matter. I'm going to get x to the 2 times n plus 1 over 2 times n plus 1 factorial. Divided by this is multiplied by the reciprocal, so a 2n plus 1 factorial over x to the 2n plus 1. Simplifying, so 2n plus 1 is 2n plus 3. So I should really write this as 2n plus 3, and this also is 2n plus 3. So look what I get. The limit as n goes to infinity, x to the 2n plus 3 divided by x to the 2n plus 1 is x squared. And 2n plus 1 factorial over 2n plus 3 factorial, you're going to get a 2n plus 3 times a 2n plus 2. And then the rest of the 2n plus 1 factorial will cancel out. Right? You're going to get a 2n plus 1 factorial and a 2n plus 1. Right? That's what we've got. And those cancel. And so as n goes to infinity, the denominator gets infinitely large, the numerator is just x squared. You get 0. It's less than 1. So just like e to the x, sine of x also converges everywhere, or the interval of convergence is everything. Or the radius of convergence is infinity, is another way of saying that. We could do the same thing for cosine, but instead of doing the same thing for cosine, we'll employ a trick. The trick is actually super nice. So, and I'll say that being able to use Taylor's formula to find the Taylor series or power series for a function is a good tool to have in our tool belt. Most of the time, we're going to try and opt for doing something that's not that, because usually using the Taylor formula is just a pain. So let's say I want to find the Taylor series, sorry, the Maclaurin series for cosine of x. Yes, we could certainly do what we did for sine. We could find all the derivatives, we could find, and then plug in 0 and get the different values. But we can also use the fact that, hey, cosine is the derivative of sine. And here's something that's nice. When you take derivatives or integrals of power series, it does not change the radius of convergence. So since we know that sine already converges everywhere, its derivative also converges everywhere. So what's the derivative of sine? Well, it's the derivative of our power series for sine. This thing here, which you can either write it that way or you can write it the long way. Writing it the long way, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. The derivative is 1 minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial. But look at this. This is just, 1. 3 divided by 3 factorial is going to be 1 over 2 factorial. So x squared over 2 factorial. 5 over 5 factorial is the 5's cancel and you get 1 over 4 factorial. And then 7 over 7 factorial is 1 over 6 factorial. So it's the same sort of pattern, just with the even powers. So you get that cosine is the sum from n equals 0 to infinity of -1 to the n times x to the 2n over 2n factorial. Which literally, if you took the derivative of x to the 2n plus 1, it would be 2n plus 1 times x to the 2n, and the 2n plus 1 would cancel with the 2n plus 1 there, and you have a 2n factorial on the bottom. So cosine of x is probably maybe not the last one we memorized, but maybe the last one memorized. There's the sum from n equals 0 to infinity of -1 to the n times x to the 2n over 2n factorial. Yeah. Sure. Converges for all values of x. Let's see where we're at here. Okay. So let's do one more example where we actually have to use the Taylor series. Sorry, it's got a little dark in here. Lighting here always feels kind of strange. I guess I can erase this list. I don't really need to leave it up. Let's erase this list. Something that I've noticed over the years, and actually, so there is a whole real theory about this, but I've always kind of noticed that the terms of sine and cosine give you the terms of e to the x if they're all positive, right? E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, et cetera, et cetera, et cetera. And cosine is all the even powers of that. Sine is all the odd powers, except that the cosine and sine are alternating. The other thing that I think is neat, I guess I shouldn't have erased it, but a sign here. So notably, sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, et cetera. And sine is an odd function. And it is not a coincidence that sine, being an odd function, has a Taylor series or Maclaurin series with only odd powers. Similarly, cosine is an even function. And when I say even function, I mean it has the symmetry about the y-axis. And not surprisingly, or not coincidentally, cosine's Taylor series approximation expansion about 0 has only even powers of x. That is not a coincidence. That is very, very meaningful. So let's do one more example that isn't easy. like the following. Let's find the Taylor series for f of x equal to the square root of x centered at 9. And I believe there is some formula in the textbook somewhere for x to the 1/2 power. I have never memorized it. It's just not something that's in my brain. So let's go ahead and just try and do this the long way. So here's what we want to get to. The sum from n equals 0 to infinity of the nth derivative evaluated at 9 times x minus 9 to the n over n factorial. So our job is to get a formula for the nth derivative evaluated at 9. So let's start taking some derivatives. First derivative, sorry, not the first derivative, the function itself. The 0th derivative is the function itself, is x to the 1/2. First derivative, 1/2 x to the minus 1/2. Second derivative, 1/2 times minus 1/2 times x to the minus 3/2. Third derivative, 1/2 times minus 1/2 times minus 3/2 times x to the minus 5/2. Fourth derivative, 1/2 times minus 1/2 times minus 3/2 times minus 5/2 times x to the minus 7/2. And it looks like we might have a pattern here. It looks like, so if I took the nth derivative, so let's see. I know I'm going to start off with 1/2 times minus 1/2 times minus 3/2 times minus 5/2 times all the way up to, let's see. So I'm trying to find a pattern here. So when n is 2, I end with a negative 1/2. When n is 3, I'm ending with 3/2. When n is 4, I'm ending with 5/2. If n was 5, I'd be ending with 7/2. So it looks like every time this goes up by 1, the fraction I end with is something over 2 for sure. And it looks like, well, the numerator is going up by 2 every time. So it looks like I'm going to have like a 2n something here. I think I'm going to have like maybe like a 2n plus 3. That doesn't seem quite right. I think it's a 2n minus 3. A negative of that. That seems about right. Let's check. If n was equal to 4, 2 times 4 minus 3 is 5. If n is equal to 3, 2 times 3 minus 3 is 3. If n is equal to 2, 2 times 2 minus 3 is 1. And if n is equal to 1, does it work here? So n is equal to 1, I get 2 minus 3, which is negative 1, but it's a negative 1, so it does work there. If n is equal to 0, it doesn't work. So this pattern only works for n greater than or equal to 1. Sometimes you have to kind of pull out the first term because you can make the whole pattern work for everything. But this definitely works for everything like that. It's kind of neat. It's interesting. So I'm looking at the notes here that I'm reading off of, and Grant wrote it totally differently, but also totally correctly. He wrote it like, so another way to see this, which I think is worthwhile, is someone else wrote it as 1/2, right? Yeah. Times, this is 1/2 minus 1. This is 1/2 minus 2. This is 1/2 minus 3, all the way to the last one here is going to be 1/2 minus what looks like, so right when the derivative is 2, I get 1/2 minus 1. When it's the third derivative, I get 1/2 minus 2. Fourth derivative, it's 1/2 minus 3. So it looks like it's 1/2 minus n minus 1. It's another way you could have done it, which would have worked just fine. So now we have to say, well, okay, that's the nth derivative x. The nth derivative at 9 is kind of terrible, right? It's not, so the problem is there's no condensed way to, well, that's not entirely true. There is a way to write this out. It is not particularly nice at all. Like there is a formula for 1 times 3 times 5 times the product of every odd number, but no one should bother trying to find it. You should just write it out the long way. So the nth derivative at 9 is just, I'm going to write it this way. Am I going to write it that way? I don't know. It seems terrible either way. Yeah. 1/2 times -1/2 times -3/2 times all the way to -2n minus 3 over 2 times, oh, sorry. This last one here, I forgot an important thing. I forgot the x to the negative, let's see. This is the -2n minus 1 over 2 power. Sorry about that. So times, sorry, I've run out of room, times 9 to the -2n minus 1 over 2, which is gross. So then the whole thing, I don't really want to write it, but I'm gonna. You have to throw all of that in right there. So here's the Taylor series formula for this particular one. It's really gross. It's the sum from n equals 0 to infinity of this giant mess. You know, so 1/2 times -1/2 times -3/2 times all the way to -2n minus 3 over 2 times 9 to the -2n minus 1 over 2 times x minus 9 to the n over n factorial plus, right, because that was only good for n. Oh, so really this formula is only good for n greater than or equal to 1. So I really have to start it at 1, not at 0. And then I have to tack on in front the 0th term. So the 0th term being f of 9. Which would just be 3. So it's not pretty. We usually try to avoid doing all this if we can, but this is what we get. If you really wanted the Taylor series for the square root of x centered at 9, this would be it. Hopefully no one ever asks you for that, although someone probably will, or something like it. Okay, so let's get back to the less terrible things. So now we've got some more Taylor series in our arsenal. We can then do things the fast way, for lack of a better phrase. For example, I want to find the Maclaurin series for, say, f of x equal to, what do we got here? Where'd you go? X e to the x cubed. I definitely am not going to do this the long way. I'm not going to try and find, right? The function is what it is, the first derivative, right? Even the first derivative starts getting messy. I have to use the product rule. It's 1 times e to the x cubed plus x times e to the x cubed times 3x squared, which is e to the x cubed plus 3x cubed e to the x cubed. That's just my first derivative. To have a chance of finding a reasonable pattern. Well, actually, you probably could find a reasonable pattern here because you might luck out and get lots of things being 0. It's not the point, though. Even if you could, I guess you probably could. I don't know. It seems iffy. But we're not going to do that because here's what we know. We know that the series for e to the x, which I'll call g of x for a moment, is 1 plus x squared over 2 factorial. Here's the thing. We can replace x with really anything we want. So g of x cubed is e to the x cubed, which is 1 plus, instead of x, I'm going to write x cubed. X cubed plus x cubed squared over 2 factorial plus x cubed over 3 factorial, and so on and so on and so on, which we could write as 1 plus x cubed plus x to the 6th over 2 factorial plus x to the 9th over 3 factorial. And we can even write it as the series, I know we're not done yet, of x to the 3n over n factorial. But then we also want to multiply by x. So then we have x times g of x cubed is x times e to the x cubed. I'm just multiplying that by x. So it's going to be x plus x to the 4th plus x to the 7th over 2 factorial plus x to, my pluses, sometimes I don't make them like x's. X to the 9th over 3 factorial, sorry. I'm adding 1 to the power. So the Taylor series for this sine zero, or the Maclaurin series, is just the sum from n equals 0 to infinity of x to the 3n over n factorial times x, or x to the 3n plus 1. And here's the great thing. Plugging in x cubed for x doesn't change the interval of convergence since it was already everything. And multiplying by x doesn't change the interval of convergence. So this converges for all x. And this is the trick or method that we employ a lot for trying to find a Maclaurin series for some kind of conglomeration of known series. Is we can multiply by x or x to any power. We can replace e to the x with, right, we can replace the x with an x cubed to get e to the x cubed. And we don't have to do all this finding of derivatives and plugging in the center to find the pattern for the nth derivative at 0. So that is often our plan of attack. Sorry, I'm trying to figure out which pen is the good one here. Let's look at a couple more examples. Oh, there was a question that somebody asked. So I should ask you guys, although I don't think we really have the time to get into it today. Have you talked about, I think someone asked about showing, oh, that's gross. Sorry. Got gross pen dust on my hand. About showing the convergence of a Taylor series, meaning not the interval of convergence, but actually showing that the remainder part goes to 0. Is that something you guys are doing in class? Yes, no. Am I just on mute? I think so. I mean, it's fair. It is kind of a weird thing. I think we'll try and get into that next time, just because it's kind of strange. I'll look at your guys' homework assignment and see. But I will say, for most normal functions we encounter, most normal functions, the Taylor series does converge to the function. Or I feel like that's not quite the right word. The Taylor series generated by f converges to f on the interval of convergence. Most of the time, that's going to be the case. I'll try and, there are definitely weird examples of functions whose Taylor series don't converge to them. So you can like find the Taylor series for a function, and then you can, and then sometimes the Taylor series doesn't actually converge to that function on the interval of convergence, which is, it's very kind of, it's a little heady, but we can talk about that next class for a little bit. I don't want to get too deep in those details because, I mean, they are pretty important actually, but I don't think they're super important to your success in this class. But let's look at a couple more examples. And then there was a question somebody asked from the homework, which Yeah, I think we can talk about that one for a sec. Sure. So let's do one more example here. Sometimes we multiply series together. So I want to find the first three terms of the first three non-zero terms, of course, of sine of x times cosine of x. I'll also point out before we do that, that if someone asks for the first, like let's say someone asks for the first three terms of e to the x cubed, one, they mean the first three non-zero terms. Two, doing it the long way would take a real long time because the first three non-zero terms, you're getting to the seventh power, which means you're going to have to get to the seventh derivative, which, right, if you're taking the seventh derivative, this is not going to be fun. So definitely try to get comfortable using these shortcuts where you take known known Taylor or Maclaurin series and you manipulate them in ways so that you can get what you want. So let's look at sine of x times cosine of x. So really what we're going to do is we're just going to write them out. So sine is the odd powers. So x to the first minus x cubed over 3 factorial plus x to the fifth over 5 factorial. That's probably all I really need. Times cosine, which is all the even powers. X to the 0th minus x to the second over 2 factorial plus, God, why do I keep writing my pluses as x's? It's killing me. Plus x to the 4th over 4 factorial. And again, that's probably enough to get the first three non-zero terms. So then we start multiplying it out and kind of grouping like terms. Let's say we had x times a 1. I think that's my lowest power of x. And there's no other way to get an x. I can't get an x squared because, right, I have odd powers times even powers. So in fact, I should only be able to get odd powers, right? Right. So let's try and get an x cubed. And let's see, I'm going to have x times x squared. So it'll be a minus x cubed over 3 factorial. Sorry, 2 factorial. But I also have minus x cubed over 3 factorial. And then it looks like the next term I should be able to get is going to have a fifth power because I can't get a fourth power. So let's see, this times this, be a plus x to the fifth over 4 factorial. And I also have this times this. Sorry, I know it's getting a little confusing. This times this is going to be a plus x to the fifth over 3 factorial times 2 factorial. Which seems kind of weird, right? But it is. And then finally, we also have this, x to the fifth over 5 factorial times 1. So those would be the first three non-zero terms. So it looks like I've got an x, and then I've got minus x cubed times 1 over 2 plus 1 over 6, which I can simplify as 4 over 6, which is 2 over 3. And then finally, I've got, let's see, yeah, this. So I've got x to the fifth times 1 over 24, right? 4 factorial is 24. 3 factorial is 6, 2 factorial is 2, 6 times 2 is 12. And then 5 factorial is 1 over 100, or it's 120. So putting this all together, simplifying the fractions, I get x minus 2/3 x cubed. And let's see. So if I get a common denominator of 120, this is 5 over 120 plus 10 over 120 plus 1 over 120, which is 16 over 120, which reduces to 8 over 60, which is 4 over 30, which is 2 over 15. So that'd be the first two terms of this. Sometimes there are other sneaky ways you can find things like this. Not always. So this is a very perfectly fine way of doing this. And yeah, I think that's all I want to say about that. But I'll point out that you could also have done this one using a trig identity. So another way we could have attacked this one, this isn't always an option, but sometimes it is. sine of 2x is equal to 2 times sine x times cosine x. So if I divide both by 2, sine x times cosine x is 1/2 times sine of 2x. And then we can use the Maclaurin series for sine of x, but throw in a 2x. So that's going to be 1/2. So sine of x is x plus, sorry, minus x cubed over 3 factorial plus x to the 5th over 5 factorial. This is going to be 2x minus 2x cubed over 3 factorial plus 2x to the 5th over 5 factorial, etc. If I just want the first 3 terms, here they are. And look, it's the same. 1/2 times 2 is going to give me, let me check and make sure they're the same. Yep, good. I'm starting with an x. All right. So 1/2 times 2 is x. 2 cubed is 8. 8 times 1/2 is 4. 4 over 3 factorial is 4 over 6, which is 2/3. And let's just multiply this last one out. Plus 1/2 times 2 to the 5th over 5 factorial times x to the 5th. Cancel a 2 here and a 2 here. That's 16 over 120, which does reduce to 2 over 15. Right? Right. So it's the same. So sometimes if you know a trig identity, you can kind of get somewhere faster. Oh, and then there was, sorry, I knew it. Someone did have a question about, what was it? It was 10.10, which I know is a little bit further than we're at, but applications of Taylor series, which I think is perfectly fine. 10.10, number 28. We were asked to find a polynomial that will approximate the function given with an error less than 10 to the negative third. So I know we're almost out of time, but let me go ahead and do this one. So here's the function given, and it's kind of funky. So the function given is capital F of x equal to the integral from 0 to x of the natural log of 1 plus t over t dt. And so the idea, and then they give you a couple different intervals. They give you actually, so let's do the one on the interval from 0 to 1. So we want to get a Taylor or Maclaurin, a polynomial that will approximate this. And then we want to also write the number of terms so that the error is less than, find a polynomial that will approximate f of x throughout the given interval with an error of magnitude less than 1/1000. So the idea here is we're going to use our tricks. I know that the natural log of 1 plus t is the integral of 1 over 1 plus t, which is the integral of the sum from n equals 0 to infinity of negative t to the n. Right, 1 over 1 plus t is 1 over 1 minus t, which is minus t to the n. And then that's going to be the sum of the integral of minus 1 to the n times t to the n, which ends up being the sum of minus 1 to the n. Integral of t to the n is t to the n plus 1 over n plus 1. Okay, so that's what this is. So here, and it might actually pay to write that the long way. So the natural log of 1 plus t is t minus t squared over 2 plus t cubed over 3 minus t to the 4th over 4, etc. I'm going to divide that by t. So that's going to be 1 minus t over 2 plus t squared over 3 minus t cubed over 4, etc. And so then we're trying to integrate that from 0 to x. So here's what our function looks like. It's the integral from 0 to x of this thing we just found here. 1 minus t over 2 plus t squared over 3 minus t 4, etc. And then, let me take a look here. So then we just integrate it. So we end up getting x. So I'm going to integrate and then plug in x because, like, let's be real, I need to finish up here. So integral of 1 is t, plug in the x, you get x. Integral of t is t squared over 2. So I'm going to get minus x squared over 2 times 2. And then here I'm going to integrate, I'm going to get x cubed over 3 squared. And then minus x to the 4th over 4 squared, plus x to the 5th over 5 squared, etc. So that's how we find the function. That's the function right there. And then, and I'm going to leave this till next time, but the idea is we want to bound the error, but since this is alternating, you can say that the error is bounded by the next term. So basically, we just have to find the next term that when you plug in 1, that term is less than 1,000, 1 over 1,000. So, right, 1 over 5, well, you have to go for a ways here, I think. I feel like I'm misspeaking there. Oh, I'm looking at the wrong one. Yeah. No, I'm not wrong. Yeah. So if you're doing the interval from 0 to 1, right, we basically want x to the n over n squared to be less than 1 over 1,000. So I think n has to be 32, I believe, for that to be true. Yeah, n has to be 32, which means you need to have the first 31 terms for the remainder to be less than 1 over 1,000. All right.